We're going to look at doing kinetic analysis using differential analysis for batch reactor data. And in this case, we'll be looking at a simple reaction. A plus B goes to C plus D, as shown here on the screen. The initial concentrations of A and B will be set to be equal. In particular, they're set to their stoichiometric ratio, so it's 1-to-1 stoichiometric ratio, and we're therefore going to run this experiment in a 1-to-1 ratio. And we've seen in class that this can sometimes give us some useful information. All right, if we start them at the stoichiometric ratio, they will always be at the stoichiometric ratio because whenever A is consumed, B is consumed at an equal rate, and C is formed at an equal rate to which A is consumed. So we can write an expression like the one here. And what we're interested in is determining, using these experiments, some kind of functional form for the rate of reaction. And here we'll postulate that we have what's called the power rate law, in which we can raise the concentrations of the reactants to some power, in this case alpha for A and beta for B, multiply them by an Arrhenius type rate constant, and that will give us a good measure of the rate. But in many cases, as we'll see in particular later in this course, we might be looking to fit a different kind of rate expression. So for example, a Michaelis-Menten or Langmuir-Henschel type rate expression. The differential analysis we'll talk about today is kind of uniquely helpful when you are trying to use a power rate law model. What that analysis will allow us to do is take numerical derivatives of some data in order to determine the reaction orders and rate constants, at least in an approximate sense. Okay, the last thing that we'll make use of in looking at this data are the relationship that every mole of A we consume, we form a mole of C, and in a constant volume batch reactor, that lets us write this expression in terms of the concentrations. Okay, and then finally, what we're going to need to do in the batch differential analysis is we'll just take the log of both sides of this expression. So we take the log of the rate, which is either negative dCA dt or dC dt, and then the log of this expression. And what I'll note first is that since CA is always equal to CB, we can just lump the terms under CA to the alpha plus beta power. And then finally, I'm going to call this KCA just to the gamma power, where gamma is defined as being alpha plus beta. And so this experiment will allow us to determine the value of gamma, so the total reaction order. Okay, so if we take the log of this side of the equation, then we get the log of K plus gamma times the log of concentration, since the log of a product is equal to the sum of the logs. And we can take this power down in front of the log. Okay, so now we're ready to look at the data and try to use this kind of relationship, where what we're going to do is try to plot this versus log CA and fit using a linear relationship gamma and the log of K. This is most easily done in Excel, and I have a very simple set of data here to illustrate this process. So as a function of time, there have been measurements conducted using this setup that have measured the concentration of C, one of the products, as a function of time. And from that, we can determine the concentration of A based on a mole balance, assuming we started with 0.5 moles per liter of A, as we described on the previous case. And so we just have some cells that define this. And now we want to do a differential analysis. And so the x term in a differential analysis, when we take the log of both sides, is just CA, and so we take the log of CA. The most difficult thing about a differential analysis is estimating a numerical derivative. I've used the crudest possible form of a numerical derivative, which is just a difference formula. So I'm taking delta CA between 2 points divided by delta T between 2 points in order to approximate the derivative. Okay, there are certainly much more accurate methods that don't assume this linear relationship essentially between the 2 points. So some assume a quadratic relationship. A lot of the most useful methods, it's useful if you do your experiment in a different way. So for example, taking data points at regular time intervals makes some of those methods function more easily. And so I'm going to just use this crude method with an understanding that it will give us an initial estimate for the reaction order. And then in a subsequent screencast, we'll look at how to get a better number for the reaction order and the rate constant. Okay, so I'm just taking this difference method so you can see that the values of my cells are just involve dividing the difference in the concentration of A by the difference in the time, and that gives us a dCA dt value, and then we just take the log of these cells. And then all I've done that we'll look at in just a minute is a plot of the log of dCA dt versus the log of Ca. Okay, and so that plot, we see that the slope, we get a fairly good linear fit. You can see there's some curvature. That's actually a consequence of the fact that we are using a very crude estimate to our derivatives. But if we fit a straight line to that, we get a slope of 1.93, and so that is equal to our gamma value, and we get an intercept of negative 8.33, and that's equal to the log of k. And so therefore, if the log of k is equal to negative 8.337, then k, we just take the exponential of that number and get a value of 0.0024. And that's in the units we've measured in terms of time and concentration. Okay, so we have to determine the units of time will be in seconds, and the concentration we have to work out by balancing the units of our rate expression. Okay, so we see this is an A plus B reaction. If it's elementary, we expect for gamma, for the total reaction order, to be 2. Here we get it to be 1.93 using a pretty crude estimate. Given the likely error in our sampling data and the crudity of this estimate, then we would probably assume that it's the best we can determine the reaction order is 2. We'll just mention that in the next screencast, we'll be looking at another way of determining our constants. Come back here, we've just determined that gamma is approximately equal to 1.92, and we've determined that k is equal to approximately 2.4 times 10 to the minus. And the units on k will need to be such that we get total units of moles per volume per time from this lumped term. Okay, and so this would, in effect, have units like this, where we have liters to the 0.92 over moles to the 0.92 seconds. And then when we multiply it by a moles per liter raised to 1.92, then we'll get the appropriate cancellation.